All right. Hello, everyone. We are looking at Chapter 3, Section 3.2 today, least squares regression. So, some learning targets. We should be able to make predictions using regression lines, keeping in mind the dangers of extrapolation. Calculate and interpret a residual, interpret the slope and y-intercept of a regression line, determine the equation of a least squares regression line using technology or computer output, construct and interpret residual plots to assess where a regression line model is appropriate. And that's probably where we'll end in this video, and then we'll have a secondary video for the back half of 3.2. But I'm going to continue with the learning targets. So probably in the second video will be interpret the standard deviation of the residuals and R squared and use these values to assess, as well as the least squares regression line models, the relationship between the two variables, describe how the least squared regression line, standard deviation, and residuals, other residuals, and R squared are influenced by unusual points, and find the slope and y-intercept of the least squared regression line from the mean standard deviation of x, y, and their correlation. So let's get into these regression lines. So linear or straight line relationships between two quantitative variables are common. And a regression line summarizes the relationship between these two variables, but only in a specific setting. So really it's when one variable helps explain the other. So as you can see here, we have a nice little scatter plot. We have our explanatory variable on the x-axis. We have our response variable on the y-axis. And then in the blue line is the regression line. Ooh, I'm not big, sorry. Much better, so you can probably actually see this. So the regression line is a line that describes how a response variable, or y, changes as the explanatory variable x changes. All right. Regression lines are in the form y hat equals a plus b to the x. And the y hat is a predicted value for y, given a value of x. So I'm going to plug in an x value. I'm going to come up with an estimated or a predicted y value. Y hat is all the hat, specifically why we have to use y hat, is used to denote a predicted value. So it's how they know, hey, this is a predicted value. And this is why notation is really important. If I said y equals something, well, that's telling me that I have a data point where y equals that. If I say y hat, that is an estimate or a predicted value. Right? So let's imagine we had a situation. A random sample of 16 used Ford F-150 Super Crew 4x4s was selected from among those listed for sales at autotrader.com. The data are shown in the table. For these data, the regression equation is price equals 38257 minus 0.162.9 miles driven. Predict the price of a Ford F-150 that has been driven 100,000 miles. So I'm just showing the calculator here for a quick bit. Put this data into your calculator. So you should go to L1. You should have the data for miles driven. L2 be the price. And pause this video until you get there. All right, now that you have the data typed in your L1 and L2, like I have it here, we're going to go and actually calculate this line. So we're going to go stat, calc, and like we said, we always do y hat equals, if I come here, I always have a plus b to the x. So I'm going to table down, I know number 4 says ax plus b. We want a plus bx. So I want the second one, y equals a plus b to the x. I'm going to press enter because my data is in L1, L2. And boom, actually before I even get there, I can see I did this regression line and I see, hey, I had the same exact equation. Y hat equals 38257 minus 0.1629 miles driven, or in this case, x. So that's how you do your linear regression. And then you can use this equation to actually find specific y values. So I'm wondering when it is driven 100,000 miles, that is an x value. So I'm going to take my equation, plug in my x value of 100,000 miles, and I'm going to solve for the price, which is 21,967. Sorry, $21,967. And the nice thing is to remember this is a predicted value, so that's why it is y hat or price hat. So this next subsection called extrapolation is, can we predict the price of a Ford F-150 with 300,000 miles? Well, let's go about doing it. Can we do it? Yeah, I'll take 300,000 miles, plug it in. Boom. I get this price to be negative 10,613. Now, obviously, that doesn't make any sense, right? How would the price of a car be negative? Someone's going to pay me to drive their car around. Well, it's something called extrapolation, right? Most of our data values, if you look at our data, was the miles driven was, let's see, the minimum was like 4,000, but there's nothing really more than 144,000. That was our largest value. 300,000 is significantly larger than our largest X value. So extrapolation is the use of a regression line for predictions far outside the interval of X values. So our X values were between 4,000 and like 144. This was almost double the maximum. This was more than double the maximum. So because of that, you can't use values that are outside that range that you're using this regression line for. And if you do, it's called extrapolation. So in this case, you would just say, if the problem asks, can we predict the price of a Ford F-150 with 300,000 miles on it? I would say, I wouldn't even do the calculations. I would just say, no, I cannot do this. This is extrapolation. That 300,000 miles is not within my range or my X values for this linear regression. And like this caution says, it could be as extreme to the positive, or so it could be greater than, or it could be less than those values too. All right, residuals. So in most cases, the line will not pass exactly through all the points in a scatter plot, right? If we look at, let's see, we have this line, right? We don't even hit most of those points. So our residuals is the distance, the vertical distance from the point to the line, essentially. So if I have this point, my residual will be how far I am from this point to my predicted value. So we have this fancy dancy formula for a residual. So a residual is the difference between the actual value of y and the predicted value of y by the regression line. And we have the formula, residual is actual y minus predicted. So an actual minus predicted, and you kind of see that's why it's y minus y hat. Let's go back. If my residual is positive, that means my actual is bigger. That means I'm going to be above. So these all have positive residuals, and the bottom half are the negative residuals, because that would mean that the predicted is larger. So a positive residual is the actual is bigger. A negative is the actual is smaller. So taking over, same problem, same data set. Says calculate and interpret the residual for a truck that was driven 7,583 miles. So this first data point up here. Well, I have the exact value, right? It's worth $21,994, but I need the predicted price as well. So to find the predicted price, I'm going to use my linear regression model, plug this number in. Boom, I get my price to be 26,795. Now my actual is 21. So when I do my residual, I'm going to do price minus the predicted price. So 21,994 minus 26,759. And I get a residual of negative 4,765. Basically, the negative just tells me that the actual data point is below the line in this case. Then if I wanted to interpret this residual, it would be the actual price of the truck is $4,765 less than the cost predicted by the linear regression line with x equals miles driven. So always give a little bit of context when you are interpreting. And also kind of depending on the problem, you might want a positive or a negative residual, like in a small sense. Like if I'm buying a truck, then I would want a negative residual because that means that I'm paying less than the predicted value than what might have been expected, which is kind of good for me. So there's a nice way to find these residuals on your calculator. So I want you to go into turn it on. You should have your list. You should have L1 and L2. So now we're going to put our residuals in L3. The way to do that is go second list, where you get L1, L2, L3. If you keep tabling down, there's a spot that says resid. Click that. And then I want to store this now. So I'm going to go second. Oh, not second, sorry. I'm just going to click store, S-T-O. I'm going to store it. And then where do I want to store it? I want to put in L3. So I got to go second list. I want to go back down to L3. And when I press enter, now my L3 has my residuals. And you can see that the residual for this first point is negative $4,764. They had 65 out. It's probably around, yeah, they rounded. So you can actually table over and see the exact value. We'll come back to using these residuals in a little bit. But if you ever asked to find the residual, this might not be a bad way to check your work to make sure you actually did the residual correctly, especially understanding if it's negative or positive. All right. So next subsection is interpreting a regression line. So a regression line is a model for data, much like the density curve of chapter 2. The y-intercept and slope of a regression line describe what the model tells us about the relationship between the response variable y and the exploratory variable x. A lot of words there. This box is a lot more important, I think. We know our regression equation is y hat equals a plus b to the x, bx, sorry. Y, I was thinking about my algebra 2 with all of our exponentials. So this is a linear regression. So I have y hat equals a plus b times x. A is my y-intercept, basically when the predicted value of y when x equals 0. And then b is the slope, and it's the amount which the predicted value changes when you increase x by 1 unit. We should be pretty familiar with kind of what slope is. But as you change your x by 1 unit, how does my y change? That's what my slope is. So they said, here's our equation still. Interpret the slope of the regression line first. So the predicted price of a Ford F-150 goes down because it's negative by 16.2, however you want to say this, $0.1629 or 16.29 cents for each additional mile that the truck has been driven. So the increment of adding 1x, that's one more mile driven. So I increase my x up by 1. That's how much my predicted value changes. It's going to go down. For B, it says, does the value of the y-intercept have meaning in context? If so, interpret the y-intercept. If no, explain why. So this is a point where sometimes, depending on what the regression is, like sometimes 0 just doesn't make any sense. Like it's just not possible for 0 to come up or be a useful indicator for what our x values are. Since this problem, our x is the miles driven, it's reasonable to assume that you could get a truck with no miles driven, right? That's a brand new car. So this model is still kind of showing and trying to test out how much would it be worth if there was no miles driven or if it was a brand new car. So in this case, it would be what is it? So sorry, this is a little off, but I would say the predicted price in dollars of a used F-150 that has been driven 0 miles is 38,257. So I forgot to type in how much it actually is worth. So you do want to put in what the y-intercept is, not, so you want to state the y-intercept and also give it in context. So just forgot to put that here. I'll do it right now. Mid video too, look at this. There we go. There we go. Just another hint of, hey, these are predicted values of y, so make sure you say predicted or estimated or something along those lines, so you actually show like, hey, I'm finding a p hat, this needs to be predicted. It's not an actual y value. All right. So the least squares regression line. There are many different lines we could use to model the association in a particular scatter plot. A good regression line makes the residuals as small as possible. The regression line we prefer is one that minimizes the sum of the squared residuals. So that's when basically what it's saying is like you could do a lot of different residuals. The one that we will focus on is making the residuals as small as possible. Okay. So this line is drawn in such a way that the sum of the squared residuals is as small as possible. Now, the reason why it's the squared residuals is because if the point is above this line, then the residual is positive. If it's below the line, it's negative. Well, if you added positive and negative values together, you're going to get this very close to zero. And in reality, these residuals would end up being zero. So the reason why we add the squared sum, the squared residuals, yes, the number will be larger, but they will all be positive. And therefore, when you add it, this will actually be a number, and the number is here. And yes, I know the number is really big. It's also because our y values are in the thousands, how much cars cost. But that's the smallest possible this line is drawn in such a way that the smallest possible sum of the residuals is this number. It's the smallest number. Right. So next kind of point is determine if a linear model is appropriate using basically residual plots. So we talked about this a little bit in 3.1, but you can only use this linear regression or these linear models if you actually have a linear relationship, right? You don't want to use these models if they're not. So it's important to see if they are or not. And one way to determine if they are a linear model or not is a residual plot. So basically what we're going to do for residual plots is we're going to take a residual plot, and it's a scatter plot that displays the residuals on the vertical axis and the exploratory variables on the horizontal axis. And if you did that, here it is. So we can do this on the calculator. So let's go in. We're going to start second plot by graphing. L1 is my X, L2 is my Y. I'm going to zoom 9 this. Zoom 9 is zoom stat, and I get this data point, these data here. Data point. If I wanted to, I could do the linear regression. Let's go over to calc. I want to skip over that one, go down to here. A plus b to the x, and I'm going to store in bars. So I have my click my linear grid. I want to click store. I want to go into vars, y vars function y1. Enter. Ooh, okay, let's try that again. Ooh, I don't think it's store. I think it's just y vars function y1. Yeah, So when you type this in, calc, table down to linear regression, linreg, L1, comma, L2, comma, where I want to store it is going to vars, yvar, function, y1, enter. So now when I click y equals, I have my linear regression put in there. I can graph this. Boom, I have my scatter plot and my linear regression or line of best fit is drawn. Okay. Now the question is, well, should I actually be doing this? Like, is this actually a linear model or not? The way to determine that is we're going to use a residual plot. So I'm going to go back in. I'm going to delete this line. I'm going to go back to my residual plot. This nice little green box tells me a residual plot is a scatter plot that displays the residuals on the vertical axis and the exploratory variable on the horizontal. So I have a scatter plot here. My exploratory is my L1, it's my X value. But now my Y list or my Y values, I want my residuals. Good thing for us, we've already stored our residuals in L3. So I can press enter, and now I can go back to zoom 9 it, and boom, I get my residual plot. And it should look very similar to this. All right. So now the question is as well, what does the residual plot really help me with? Well, a residual plot there's two ways. It'll tell you if the model is appropriate, if this linear model is appropriate. If the residual plot shows no obvious patterns, then it is an appropriate regression. So here, and we'll take a look at some pictures here, I think. Here is my residuals. I would have residuals on the left, my exploratory on the X. There's no pattern here, right? These points are just kind of haphazardly plotted. So because of that, a linear regression was appropriate. Here are two examples where it wasn't appropriate. Here's my residual plot to my left, and you can see, hey, this is a pattern, a parabola, more or less. There's a pattern here. So this residual plot would tell me that the linear model is not appropriate. Okay. For ours here, there's no pattern here, so it is appropriate. So, question is how to interpret a residual plot. Basically, what I just said. If there is no leftover curve pattern in the residual plot, the regression model is appropriate. If there is a curve pattern in the regression plot, consider using a different regression model or a different form, essentially. Right? So, no pattern, good. If there's a pattern, we got to try and find a different type of regression. So same idea, we have our this is the same plot we just calculated. Is a linear model appropriate? Well, yeah, there is no obvious pattern left over in the residual plot, so the linear model is appropriate. All right, and that is where we are going to stop for today. We'll pick up the rest of the chapter in the next video.